Welcome back. This video is now going to look at multiple inheritance, which is another feature that exists in C++ and is quite capable, but has a number of caveats that are worth understanding. So why do we do this? Well, remember, inheritance is a way to get code reuse. And therefore, sometimes it might be useful to inherit from two parent classes so that you get to inherit from two different collections of methods. Now, the question that arises when you do that is what's happening in terms of the memory layout, how complex is this, and what happens to polymorphism? Does it still work without any kind of changes? So let's take a look at that and try and understand. So the way we will do it is by actually looking at an example. So let's do that. I have here in a buffer an example, so let's go through it. This is basically a class that has two attributes. Oops, sorry. The class has two attributes. An int that's called x, and a double that's called d. Then it has a constructor, a default constructor, a custom constructor, and a virtual destructor. That's all there is. So clearly, A is going to be an object with 16 bytes of storage on a 32-bit architecture. Then I have B, which is another base class, so it doesn't inherit from anything. It contains a string and an array of character of size 32, a default constructor, a custom constructor that's going to actually initialize the name based on a string, and then a loop that initializes the array called code. Then the destructor is also virtual in this case and doesn't do anything really special. Finally, I have C, and that's where the fun begins. C inherits from A and B, and in both cases, the inheritance is public. So we are publicizing the fact that C inherits from A and B to everyone, to C subclass, and also to any piece of code that may end up using a C or derives classes from C. So that fact is known to everyone, and C adds its own attribute, an integer that's a length, and IA, which is an array of integer. Its constructor takes a bunch of arguments. It calls the constructor of the superclass, it takes the constructor of the superclass A as input, right? So that's what we do here. It calls the constructor of the superclass B, so both constructors are being called, and then initializes its length. After doing that, it executes a piece of code that allocates an array of integer of the prescribed length, and then copies everything that was in the integer array ptr inside the local variable ia. Now, that's all there is. Maybe we should just be good citizen and implement the destructor for C. So let's go ahead and do this. Remember, because the destructors of the parent class are virtual, mine is virtual automatically, so I don't need to do anything special. And here the one thing to do, of course, would be to invoke the delete operator on the array IA to make sure that the memory for this array gets recycled. Now that this is done, let's go ahead and look at the test program. So what you see here is a main function that declares an array, a fixed array T, with the value 1, 2, 3, 4, 5. And then it creates a C object passing 42, the value pi, the string Joe, and then the value 5, which is the length of the array T, and the array T itself. Once I have created that C, I hold its address inside the pointer to an object of type C. And that pointer we call P. Then what I do is that I print out the pointer to make sure everything is okay. Note that this is just printing out the pointer and not the object. Then I'm putting P inside two variables of type A pointer and B pointer. And I print again the pointer AP and BP. And for good measure, I simply ask to print the size of all three classes, A, B, and C, by using the size of operator, right? So that's all this program does. Nothing really special. It already uses multiple inheritance, but what I want to highlight is what's happening in terms of memory layout when we do this. So let's take a look and run this program. So I go into my Scratch buffer. No, not my Scratch, my shell buffer, sorry. And we're in ModJ, so let's go back up to mod I. And I have my what's the name of the file? Min-h. So let's compile C++ min-h.cpp minus o min-h minus std C++14. That's done. Now I run min-h, and here's my output. I get the pointer p, and pay attention, there are lots of digits, but it ends in 3330. When I print the value of AP, remember what AP is, right? AP, sorry, min-h. AP is just the result of doing this assignment, of assigning P to a pointer of type A star. So I'm just seeing my object of type C as an object of a supertype. And when I print AP, the pointer is the same, it's 3330. Now when I do the same assignment with a B, then I'm getting a different pointer. Oh my God, it means that the assignment changes the value of the pointer. And notice that the size of the three classes are vastly different. 24 bytes, 64 bytes, 104 bytes. So let's try and understand what happened when we did that. Let me draw for you, and we are going to actually do that, put the code of A and B straight on the screen. First, draw an A instance. So here's my A object. So it has an int and a double, and it has a virtual method. So if I had an A, just an A instance, here is what it would look like. I would have an object, I would have a pointer to a table of size 1 that has the pointer to the destructor. And then the attributes here would be an integer underscore x, so I will put its name, and then a double underscore d. That's what an A looks like. That's what an A looks like. Agreed? Now, let's do the same thing, but drawing a B. What does a B look like? Well, we have the definition here, and remember that B has a virtual destructor as well, so it has two fields, but this time it's a string and an array of characters, so a B is quite a bit bigger, actually, so let's make a bigger object. The first field is a pointer to a table of size 1, because there is only one virtual method, and that method happens to be the destructor of B, right? Tilde B. So that's my destructor. Here it was tilde A. Now the attributes are what? There is a string called name, and then there is code, which is an array of 32 characters, and we call it code, right? That's what we have when we have a B. Now the question is, what happens when you create a C, right? Which is here. That's my declaration of a C. What's happening when we do that? Well, first, we inherit publicly from A and B. You have the picture of an A, you have the picture of a B. Notice that there are two VTBLs. Each one has a VTBL. So what's happening when we do that? Well, what's really happening is that we're going to take the representation of that and concatenate them in memory. And then we'll have the attributes of C behind. So let me draw, and I will do that here, a fairly big box. Maybe I'm going to change color because that's not very readable. So sorry about that. And it's hard to erase on top. So let's do a bigger box. Okay, that's better. Squeaky, squeaky. I have a VT, a pointer to a VTBL here. Okay, so I have that pointer to a table. And just to make it completely clear, I'm not even going to draw it like that. Well, yeah, I'll draw it like that. And it's pointing to my tilde A destructor, right? Then I have an X, and I have a D. This is not drawn to scale, but it gives you the idea. Then once I have that, I gotta have a B. So now I'm going to put this and put it here. So I'm gonna have a pointer to another VTBL. And this one will have the destructor of B. So far, so good? So once I've done that, that's cool. But now I need to actually add a number of things that are the attributes of that. So I will have a name and then a code that's slightly bigger, right? So I have name and code that come here. And now finally I get to define my C. So for C, I need, well, a VTBL, But the good thing is that we know that the VTBL should be the first field of the object. So this VTBL should actually contain not the destructor of A, that is change. What it should contain is a pointer to the destructor of C. So that's what we get in reality. So that is gone now, right? That's what I really have. Now, what else do I find after I have put the destructor in this VTBL? I find out that I need two attributes, len, which is an integer, and ia, which is a pointer. So I get len, and I get ia, which is a pointer. Now, when I will call the constructor on this object, ia will get initialized to an array that's allocated on the heap, right? Because that's what we see on this line of code. This line will allocate, but when we are just creating the object, this doesn't happen. So this is what we have. I want to attract your attention to the fact that I have, even though I had 3 classes, I have only 2 VTBLs. In particular, I ended up reusing the VTBL of A because A was listed first. I inherit from A, then B. A was listed first, so the VTBL of A is reused and is modified because the method is polymorphic, so that we have the destructor for C in the first entry of that VTBL. Now, when I look at further down, I get another VPTR, but this one is really for the destructor of C, and then I find my other methods. So this is what happens. Now, why do we see this funny behavior that when we do these kinds of assignment, like here, these 2 assignments, that the pointer is changing? Well, that's because when you have a pointer to a C, you have a pointer here. That's a pointer to a C. It's a pointer to the beginning. Notice that an A is exactly at the same place. So an A star or C star are both pointing to this place. A star and C star are both pointing to this place. But if you convert P, which is a C star, into BP, which is a B star, we need to be at the beginning of an object of type B, and the beginning of an object of type B is here. So that's where a B star would start. So you see that when you do something as innocuous as an assignment of pointer, the value of the pointer actually changed. It went from one address to another, and the distance between the two is none other than the size of an A. That's exactly the displacement to get at the beginning. So you get this funny behavior when you are actually running methods on this object, depending on whether you're running a method of A or a method of C or a method of B, the value of this, remember this, the implicit name, the value of this will change. Because if you're running a method that's defined exclusively on A, it should be that address. If it's a method on C, it should be also this address. But if it's a method of B, it should be that address, so that we pick up the correct VTBL. So based on that, the pointers here are changing. And if you were to actually invoke a method, the value of this would be changing depending on which method is invoked. Note that it's still polymorphic. When we delete that thing, even though we only know it's an A star, when we delete it, we will go to A star table and invoke the destructor there, which knows, hey, I'm dealing with a C, that's the real destructor that I need to actually run, and I will get the proper behavior. So that's what's going on with this. You have a slightly funny memory layout to actually set up everything, but it does work at a cost, right? You have extra complexity, and you can no longer make a key assumption that the value of this never changed. Here, the value of this will change from method to method depending on where you got the method from. If you got it from an A or a B, the value of this will be different. And therefore, you can never make the assumption that the value of this is invariant. It does change depending on the circumstance. So that's it. That's what I wanted to do on multiple inheritance. One more little caveat, and then we're finally through with this entire topic of inheritance and all the subtleties that are associated to it. See you next time.